Black holes are among the most fascinating objects in the universe. They are regions of space-time where gravity is so strong that nothing, not even light, can escape. These cosmic monsters form when massive stars collapse at the end of their lives. In the 1970s, Stephen Hawking made a groundbreaking discovery. He showed that black holes are not entirely black. They actually emit a faint radiation, now known as Hawking radiation. This discovery led to a profound puzzle known as the black hole information paradox. According to quantum mechanics, information cannot be destroyed. However, if black holes evaporate through Hawking radiation, what happens to the information they swallowed? This question has puzzled physicists for decades. It challenges our fundamental understanding of the universe. Hawking radiation arises from the bizarre world of quantum mechanics. At the edge of a black hole, called the event horizon, pairs of virtual particles are constantly popping in and out of existence. Normally, these particles would annihilate each other almost immediately. But near a black hole, one particle can fall in while the other escapes. The escaping particle is what we observe as Hawking radiation. This radiation carries away a tiny amount of energy from the black hole. Over an incredibly long time, this process causes the black hole to slowly evaporate. Think of it like a pot of water simmering on a stove. The heat, or Hawking radiation, slowly causes the water, or black hole, to evaporate. The black hole information paradox arises from a fundamental conflict between general relativity and quantum mechanics. This paradox has puzzled scientists for decades, challenging our understanding of the universe at its most fundamental level. General relativity tells us that black holes are simple objects. They're described by just three properties: mass, charge, and angular momentum. They are completely characterized by their mass, charge, and angular momentum. This simplicity is elegant, yet it hides a deeper mystery. Quantum mechanics, on the other hand, insists that information cannot be destroyed. Every particle, every interaction, every quantum state must be accounted for. This principle is known as unitarity, and it is a cornerstone of quantum theory. This principle is crucial to our understanding of the universe. It ensures that the past can be reconstructed from the present, that no information is ever truly lost. It ensures that the past can be reconstructed from the present. But what happens when we introduce black holes into the equation? If black holes evaporate and disappear completely, what happens to the information they contained? According to Stephen Hawking's theory of black hole radiation, black holes can emit radiation and lose mass over time, eventually evaporating entirely. Does it vanish from the universe, violating quantum mechanics? Or is there a way for this information to be preserved, even as the black hole itself disappears? Or is there a mechanism by which this information is preserved and released? Some theories suggest that information might be encoded in the radiation emitted by the black hole, a concept known as the holographic principle. This is the heart of the paradox, a puzzle that has profound implications for our understanding of the fundamental laws of physics. Resolving this paradox could lead to a deeper understanding of the universe, potentially unifying the theories of general relativity and quantum mechanics into a single, coherent framework. Section 4. Quantum entanglement, spooky action at a distance. Quantum entanglement is one of the most fascinating and perplexing phenomena in the realm of quantum physics. It challenges our understanding of the universe and the very nature of reality itself. One possible solution to the paradox lies in the strange world of quantum entanglement. This concept suggests that particles can become entangled in such a way that the state of one particle is directly related to the state of another, no matter how far apart they are. This phenomenon, which Einstein famously called spooky action at a distance, allows two particles to become linked, even if they are separated by vast distances. When one particle changes its state, the other particle instantaneously changes its state as well, defying the classical notion that nothing can travel faster than the speed of light. Imagine two coins flipped simultaneously, one landing on heads and the other on tails. In the classical world, the outcome of one coin flip has no bearing on the other. However, in the quantum world, these two coins could be entangled. Even if these coins are light years apart, they remain correlated. This means that if you observe one coin and find it to be heads, you'll instantly know that the other coin is tails, regardless of the distance between them. If you know the state of one coin, you instantly know the state of the other. This instantaneous connection between entangled particles suggests that information can be shared across vast distances without any delay. This interconnectedness between particles, even over vast distances, suggests a way that information might escape from a black hole. The idea is that the information swallowed by a black hole could be encoded in the entanglement between particles inside the black hole and those in the escaping Hawking radiation. Could the information swallowed by a black hole be encoded in the entanglement between particles inside the black hole and those in the escaping Hawking radiation? This theory, while still speculative, opens up new possibilities for understanding the nature of black holes and the fundamental principles of quantum mechanics. It challenges our current understanding and pushes the boundaries of what we know about the universe. Section 5. Nonviolent nonlocality, a bridge between two worlds. This section delves into the fascinating intersection of quantum mechanics and general relativity, two pillars of modern physics that often seem at odds with each other. The concept of nonviolent nonlocality offers a potential bridge between these two worlds, providing a new perspective on the nature of black holes and the information paradox. Physicist Stephen Giddings has proposed a compelling solution to the paradox called nonviolent nonlocality. This idea is a significant step forward in our understanding of black holes and the fundamental laws that govern our universe. Giddings' work is not just theoretical, it has practical implications for how we think about information and its preservation in extreme conditions. This hypothesis suggests that information can leak out of a black hole without violating the principles of either general relativity or quantum mechanics. Traditionally, it was believed that anything falling into a black hole was lost forever, but Giddings' theory challenges this notion. By proposing that information can escape, he opens up new avenues for research and exploration. Giddings argues that while the interior of a black hole is inaccessible to an outside observer, information about its contents might be encoded in subtle correlations within the Hawking radiation itself. This means that even though we can't see inside a black hole, we might still be able to learn about what it contains by studying the radiation it emits. This idea builds on the concept of quantum entanglement, suggesting that the entanglement between particles inside and outside the black hole could provide a channel for information to escape. Quantum entanglement is a phenomenon where particles become interconnected in such a way that the state of one particle instantly influences the state of another, no matter how far apart they are. Think of it like a message in a bottle. Just as a message can be placed in a bottle and cast into the ocean, information can be encoded in particles and sent out from a black hole. This metaphor helps to illustrate the complex and often counterintuitive nature of quantum mechanics. The bottle or black hole might be irretrievable, but the message or information can still reach the shore, the outside world. This concept not only provides a potential solution to the information paradox, but also deepens our understanding of the universe's most mysterious objects. By bridging the gap between quantum mechanics and general relativity, nonviolent nonlocality offers a glimpse into a unified theory of physics.